Good afternoon, ladies and gentlemen. It's a great pleasure and privilege to be here, and I'm grateful to the organizers for this opportunity. This talk is co-authored by Sir Charles, and also by Masataka Nakazawa from Tohoku University, and by Professor David Payne, second row here from Southampton University. Now we shall start with the paper that caused the trouble of the internet, and that's Charles Kao and George How presented in '66. I will not go through the abstract, but it looks like extremely simple abstract, and the more simple, the more fundamental, if it's a new paper. And it's a fiber design which can transmit single modes at optical frequencies, and there are some considerations about loss, bending loss, radiation loss, and other things. This paper you can certainly find, and I will not go into deeper details. What is important is the conclusions, the key conclusions, again, the very simple conclusions, but extremely daring. One can do a fiber waveguide depending on the availability of suitable low-loss dielectric material. And that's the identification of the key issue. What should be that material? Difficult choice, but not impossible. So the experts say it's impossible, and as Charles says, it's not impossible. So we know from that it was possible. And certainly, one should be able to do 20 dB per kilometer or less in order to have a fiber. 20 dB is 1% transmission. And that's basically what happened. This is the absorption spectrum of the fiber of silica glass through the years, from the '66 paper to early 1873 to 90. You can observe that the loss has been successively decreased, making new windows appear, going progressively to the far infrared and reaching the rock bottom predicted by Rayleigh scattering, which is the absolute unavoidable variations of the density of glass in the purest material possible. And that reaches now 0.2 dB per kilometer, that is 20 dB per 100 kilometers. So the vision was right, a bit pessimistic, but on the right direction. I'm going to speed up a little bit now we are in the mid-80s, and the experts would say fiber optics, very simple. We have the transmission window at 1.5 micron. We have the best receiver, phase shifting, homodiode detection. That's the quantum limit. We need 9 photons per bit to have a beta rate of 10 to the minus 9. And depending on the bit rate, this defines, if you forget the dispersion issue, that's an engineering design issue, this is a rock bottom. This is quantum. This is you don't joke with quantum. This is quantum limit. And 1 gigabit, the maximum distance is about 300 kilometers. And that's it. After that, you need to have something that's called a repeater. A repeater, here's the basic outline of a system. You have Charles Kao's fiber, idealized and that's realistic in mid-85. 0.2 dB per kilometer, so you can go 1 gigabit, also around 100 kilometers. And you have this monster here that is an ugly device that kills a photon to change it into an electron, and a beautiful laser that changes an input electron into a beautiful photon. So this is kind of for a long time it has been the unavoidable design of a long distance transmission system. You need as many repeaters as you want to go. If you want 1,000 kilometers, you need 10 repeaters, or 200, whatever, depending for crossing the Atlantic. And there is it's just for one wavelength. The modulation format is fixed. The bandwidth is limited by the electronics. You could think of the faster electronics, but that doesn't go owing to the complexity. You won't go very fast into the 100 gigahertz and all this complex, costly, and not compatible with the carbon dioxide view of the world. Now, say I'm an operator and I want to design a long cable which would have 40 gigabit of payload that would use 16 channels, 16 lasers. So this is all the stuff I need to put in my cable. 16 fibers, my 16 transmitter, my 16 receiver, no problem. 16 fibers, 16 repeaters, and I have to repeat that every 50 to 100 kilometers. And I have to feed this monster with electricity, and that is going to cost me a significant amount. And that's the way it was done. Now comes something really of the kind of miracles that we like in this laser community. Back to Albert Einstein, stimulated emission. If you dope a short segment of the fiber with some kind of laser ion, that is a dopant that can be excited by an external laser into the upper state, then you store the energy, and by stimulated emission, a weak signal input would do an avalanche of photon multiplication by stimulated emission to be amplified into a strong output. I put a rainbow to show that it works at any color of the spectrum that fits within the spectrum of the laser line, which is broadened by some mechanism. So regardless of the wavelength or the color of the signals, that propagates. There's nothing else. Well, there is a little laser here, a pump source. So, of course, there is an amplifier in the laser, and here there is a laser in the amplifier, but it's a pump laser. Here are a group of crazy guys, the Southampton group led by Professor David Payne at Southampton, that really initiated all this activity with the new process of doping fibers with rare earth ions, including erbium, having the vision, the Southampton vision that 1.5 micron happened to be an erbium laser line. Erbium, the glass doped with erbium has a 1.5 micron fluorescence. Then it could be used for telecoms. And it's a broad spectrum, so it could be used to amplify several signals at once. Here are the collaborators from Southampton, and this is me hiding behind the protective glass because that's a 2-watt argon laser with a 1 meter of dope fiber, and as you can see, we use gas laser and all the kind. Impractical. Everybody says this is no way you can do telecoms with that. We have heard everything that you can imagine of that nature. Assume now that you have a practical pump source that could be a laser diode, a few milliwatts, and that piece of dope fiber will be so sensitive that only a few milliwatts could provide 20 dB of gain. 20 dB, the loss of 100 kilometer fiber. Then you have a seamless propagation of the signal in the optical waveguide, and once in a while, a short strand, a few meters of dope fiber, pumped with this miniature laser, with the gain providing the exact compensation of the loss of the preceding segment. As it turned out, the group led by Professor Nakazawa, then at NCT, managed to demonstrate the first LD pump laser diode pump EDSA by the early '89, and that was it. The whole thing would fit into a small box, not bigger than a cigarette pack, and the few milliwatts would provide even 30 dB gain, and that basically provides. I think I missed that one. This is an artist view of the Erbium-doped fiber gain. It has to be flattened a little bit with filters, but the idea is there. Now, I want to do my 40 gigabit system with 16 channels at 2.5 gigabit. I just put the equivalent of a prism, a wavelength combiner, and a wavelength splitter. I have only one fiber with as many amplifiers along the line. Sounds like a very simplified design, especially because it carries the channels at any bit rate that can fit in the spectrum with any modulation format, assuming that the fiber remains linear, which is another story, and assuming also that the fiber has dispersion being compensated somewhat